Hello, this is the 13th video on my multivariable calculus. In this video, we're going to talk about the chain rule. So let's first revisit the chain rule in single variable calculus. So if you have a function of y that is a function of u and u is a function of x, then the chain rule tells us that derivative of y with respect to x is derivative of y with respect to u times derivative of u with respect to x. This is one way of writing down the chain rule. Now, this is a particularly good way of writing down the chain rule because then we can extend this to multivariable functions. Okay, so let's look at a few examples. We're going to explore how to do the chain rule using a few examples, and then at the end of the video, we're going to talk about implicit differentiation, and that's basically it for this video. Okay, so suppose z equals f of xy and x equals g of t and y equals h of t. We want to evaluate the derivative of z with respect to t. So the first thing we're going to do when we apply the chain rule is we're going to draw a diagram. Z is a function of x and y, and each of these are functions of t. In order to evaluate the derivative of z with respect to t, we'll have to start from z, called the root of this tree, and end with the variable t, which is what we're trying to differentiate. We're going to go along these paths from z all the way to t. There are two such paths. For each one of them, we are going to take the derivative. So this would be partial z with respect to x, partial x with respect to t. Although because x is only a function of t, we could also write this down as the regular differentiation. Derivative of y with respect to t and partial of z with respect to y. So here is how the chain rule works. We are going to go along each of these paths. We are going to write down the derivatives and multiply. So in the first path, we get partial of z with respect to x times derivative of x with respect to t. Along the second path, we get partial of z with respect to y times derivative of y with respect to t. Partial of z with respect to x would be partial of this function with respect to x. So that would be f sub x, partial of x with respect to t, or just the regular derivative of x with respect to t, that's g prime of t, plus partial of z with respect to y, that's f sub y, and derivative of y with respect to t. So that's h prime of t. So dz dt is exactly this. Okay, so let's do one more example. Given that z is a function of x and y, x is a function of t, and y is a function of t, we want to evaluate the derivative of z at t, z with respect to t at t equals 1. So the diagram for this one is actually quite similar. So z is a function of x and y. X and y are both functions of t. So what we do is we're going to start from z, end with t, and we are going to look at all the path from z to t. So derivative of z with respect to t is going to be partial of z with respect to x times derivative of x with respect to t plus partial of z with respect to y times derivative of y with respect to t. So this is not significantly different from the previous problem. Now we're going to evaluate these by just using rules of differentiation. Partial of z with respect to x, we have to take the derivative of this one with respect to x, but it's a partial, so this would be 2x natural log y. This is partial of z with respect to x times derivative of x with respect to t, so that would be 3t squared plus partial of z with respect to y. X squared is constant, derivative of natural log is 1 over y, and then times derivative of y with respect to t. In order to evaluate derivative of y with respect to t, we will have to use the product rule. So first one times derivative of the second one plus derivative of the first one times the second one. So this is the derivative of z with respect to t. Now they said evaluate t equals 1. Evaluate this at t equals 1. So if t equals 1, then x would be 1 cubed, which is 1, and y would be 1 times sine of 1, which is sine of 1. So now we're going to take this and we're going to plug in and plug those into the derivative. So derivative of z with respect to t at t equals 1 is equal to 2 times 1, so that's 2, times natural log of sine of 1, so that's 2x natural log of y times 3, and then times 1 squared, because t is 1, plus x squared, which is 1, over y, which is sine of 1, times 1 times cosine of 1 plus sine of 1. So to simplify, there's not much we can simplify, but we can just multiply basically 2 and 3. We get 6 natural log of sine of 1 plus cosine of 1 plus sine of 1 divided by sine of 1. So this would be our answer. Okay, so let's do one more example on the chain rule. So here is another example. We have z as a function of x and y. We'll start from drawing it a tree diagram. So this is a function of x and y is a function of x, and we are trying to find the derivative of z with respect to x. Okay, so one way would be to substitute this x in here and then differentiate. That's definitely an acceptable method, but we would like to learn the chain rule. That's why I'm not going to do it that way. It also is going to be a little bit more complicated. So starting from x, z, we have two different paths that start from z and end with x. So we are going to write down the formula for each one of them. So dz dx is going to be partial of z with respect to x. So that would be the first one. So this is partial of z with respect to x. So that's one of the terms. The other one is partial z with respect to y, and then derivative of y with respect to x. So plus partial z with respect to y times derivative of y with respect to x. Partial of z with respect to x, we have to take the derivative of x squared plus 2y squared with respect to x. That would be 2x plus partial of z with respect to y, that would be 4y times derivative of y with respect to x, which is 1 plus 1 over x. So dz dx is going to be 2x plus 4y plus 4y over x. So this would be the solution to answer to this problem. Okay, so let's do something a bit more complicated. Given w is xy plus z, x is u squared plus v squared, and y is natural log of u plus v, and z is 2uv, we want to find the partial of w with respect to u and second partial of w with respect to v and u. Okay, so again, we're going to draw the tree diagram. That's the key for all of these problems. So w is in terms of x, y, and z. X is in terms of u and v. Y is in terms of u and v as well. And z is in terms of u and v. Now the first one is partial of w with respect to u. So we'll have to start from here and end with u. So let's see how many different paths do we have that starts from w and ends with u. Well, we have two of them here, one here, and then one last one here. So there are a total of 3 paths that start from z, w, and end with u. Okay, so let's write down one term for each, and then we'll do the calculation, and eventually we'll have to plug in u and v equals 1. So partial of z with respect to partial of w with respect to u. So that would be partial of w with respect to x times partial of x with respect to u. So the first one right here is partial of w with respect to x. This one is partial of x with respect to u. This one is partial of w with respect to y. And this one is partial of y with respect to u. Partial of w with respect to z. Partial of z with respect to u. So we'll write down all of them, multiply them, and add them. So partial of w with respect to z times partial of z with respect to u. We'll evaluate these and then we'll plug in the values that they gave us. Okay, let's start from partial of w with respect to x. Partial of w with respect to x is we have to take the derivative of this one with respect to x, but it says this is partial, so this would be y times partial of x with respect to u, so that would be 2u plus partial of w with respect to y, so we have to take the derivative of this one with respect to y, partial of that with respect to y, so that's x, partial of y with respect to u, so y is natural log, derivative of that is 1 plus u plus v, and the inside is u plus v, so the derivative of u plus v is just 1, plus partial of w with respect to z, which is 1, times partial of z with respect to u, which is 2v. So this is partial of w with respect to u. Now they said u and v are equal to 1. In order to be able to evaluate this one, we need to find x and we also need to find y. So let's see what x and y were. X is 1 squared plus 1 squared, which is 2. And y is natural log of 1 plus 1, which is natural log of 2. We'll take these and we're going to plug it into the partial that we found. So partial of w with respect to u at u equals v equals 1 is equal to y times 2 times 1. So that's 2 natural log of 2 plus x is 2 over 1 plus 1 plus 2 times 2. So this one would be 2 natural log of 2 plus 3. So this is the partial of w with respect to u at u equals v equals 1. So the next one was the second partial of w with respect to vu. So this was the question. This is the same as partial of w with respect to u, and then partial of that with respect to v. Now, we already evaluated partial of w with respect to u. So let's write this down here so that we can write down the tree diagram. Partial of w with respect to u as evaluated is, we evaluated right here. So this one is partial of w with respect to u. So let's write it down here. 2uy plus x over u plus v plus 2v. Okay, so let's write this down. This function is a function of x, y, u, and v. We have all of these involved. X is a function of u and v, and y is also a function of u and v. So how many paths do we have that starts from this function and ends at u? So the end must be u, and the start would have to be the function partial of w with respect to u. Although no, they said partial with respect to v, so we'll have to end with v. So this would be the end here. Okay, so I have to go along these paths. This is the first one. This one is the second one, and this one is the third one. So second partial of w with respect to vu is equal to, well, first we'll have to take the partial of this with respect to x. So what is partial of this with respect to x? Well, we have to take the derivative of 2uy with respect to x, that's 0. X over u plus 1, u plus v squared, that's negative x, that's 1 over u plus v. We are taking partial of that with respect to x, that's 1 over u plus v, and then 2v equals 0. 2v, partial of that is equal to 0, times partial of x with respect to v. So we took partial of the initial one with respect to x. Now we'll have to multiply by partial of x with respect to v. So let's see what x was. X was u squared plus v squared. Partial of that with respect to v is in fact 2v. So that's the first term. Plus, next one is partial of that with respect to y. Well, partial of 2uy is 2u with respect to y. X over u plus v is 0. 2v is also 0. Then we'll have to find the partial of y with respect to v. Well, y is given as natural log of u plus v. So that would be 1 over u plus v. And finally, we'll have to find the partial of that with respect to v. So what is partial of that with respect to v? Well, partial of 2uy is just 0. Partial of x over u plus v is negative x over u plus v squared. And then partial of v, 2v with respect to v, that is just 2. So now, at u equals v equals 1, we would get the second partial of w with respect to vu is equal to 2 times 1, u and v are 1, over 1 plus 1, plus 2 over 1 plus 1 again, minus, well, we found x before, x was 2, so 2 over 1 plus 1 squared plus 2. And then we can simplify this. This is going to be 1 plus 1 plus 2, that's 4, minus 1 half. So that is 7 over 2. So that's the second partial of w with respect to v. U at u equals v equals 1. Okay, so the next thing we're going to do is we are going to look at implicit differentiation. Okay, so we're going to relate this with implicit differentiation. So imagine we have a function y of x, but we don't know the explicit formula for y as a function of x. But what we do know is a relation between x and y. So this relates equals 0, relates x and y as a function of y, of x. So now the objective is to find derivative of y with respect to x. Okay, so how do we do that? So first of all, if you look at f as a function of x and y and substitute y in terms of x, that would give us 0. So now let's look at this function. Let's look at the function f of x comma y. This is a function of x and y is a function of x. We would like to write down the partial of f with respect to, or the derivative of f with respect to x. So derivative of f with respect to x is equal to partial of f with respect to x plus partial of f with respect to y times derivative of y with respect to x. Now, notice that f as a function of x only is exactly 0. So what does it mean? It means on the left side of this equality, I just have derivative of 0, which is 0. So 0 equals, let's for simplicity write this down as f sub x plus f sub y dy dx. Now if we solve for dy dx, we're going to end up with negative f sub x over f sub y. And this is the formula for implicit differentiation. So part derivative of y with respect to x is negative f sub x over f sub y. So let's do an example on this. Given the relation this, we want to find derivative of x, y with respect to x. So if we write this equality in this form, minus 3xy equals 0, this would be our implicit relation here on the left. This is our f of xy. So what we could say is derivative of y with respect to x is equal to minus f sub x over f sub y, which is minus, we have to first differentiate this with respect to x, so 3x squared minus 3y, and divide that by 3x squared minus 3x. So there's a 3 on top that we can simplify, so we get x squared minus y over y squared minus x. So dy dx is going to be y minus x squared if we distribute the negative sign over y squared minus x. So that's how we can do implicit differentiation. To summarize, what we did was we learned how to evaluate partial derivatives using the tree. So we draw a tree the root of the tree would be our function, and then we put all of the variables that that function is in terms of, and then we'll keep doing that, and then we write down the relation for partial derivatives. And then we learned how to evaluate derivatives using implicit differentiation. I will see you in the next video.